that was that epic. I'm still just drinking my coffee, so I'm not quite there yet. I know you expect a lot from me, but just chill out, okay? My microphone's over here, so you're not really getting the sound. So yesterday, I was on here, and I didn't realize that my sound from my second laptop over here had multiple input sources for the sound, and that all of the input from that was basically adding double echo. So that was awesome. Love that. But it's fine, because we're here, probably here for like an hour or so, maybe a little more. And that's more of the best statistics videos you've ever seen in your life. It's what I do here. I'm just trying to get a little smarter, a little more thoughtful. So welcome. This lady's name is Adrian Hill. I'm not going back. I'm not watching all the other videos. We're gonna crush this series. I'm not watching all the other videos again just because the sound is crap. That's staying up online for posterity. So we'll have to deal with that. But we're gonna keep going, and I think I've fixed my sound. So we're just gonna get into it. Remember, statistics. Actually, another thing I might want to do today is cover the what's it called? The Stanford Encyclopedia of Philosophy's article on the philosophy of statistics. I think we need to ground our understanding in statistics in more depth. So I want to cover that as well and take some notes. Super exciting stuff, I know. Listen. This is what you're here for. To get the smarts. And that's what I aim to peddle. Okay? Alright, let's get into it.
We spent a lot of time talking about data visualization and different kinds of frequency plots, like dot plots and histograms. They tell us how frequently things occur in the data we actually have. But so far in this series, the data we've talked about isn't all the data that exists. If I want to know about student loan debt in America, I'm definitely not going to ask over 300 million Americans. I'm just lazy like that. But maybe I can find the time to ask 2,000 of them. Samples and the shapes they give us are shadows of what all the data would look like. We collect samples because we think they'll give us a glimpse of the bigger picture. They'll tell us something about the shape of all the data. Because it turns out we can learn almost everything we need to know about data from its shape. Picture a histogram of every single person's height. Now imagine the bars getting thinner and thinner and thinner as the bins get smaller and smaller and smaller, till they're so thin that the outline of our histogram looks like a smooth line, since this is a distribution of continuous numbers, and there's an infinite possibility of heights. I am 1.67642 and on meters tall. If we let our bars be infinitely small, we get a smooth curve, also known as the distribution of data. A distribution represents all possible values for a set of data, and how often those values occur. Distributions can also be discrete, like the number of countries people have visited. That means they can only have a few set values that they can take on. These distributions look a lot more like the histograms we're used to seeing. Like a histogram, the distribution tells us about the shape and spread of data. We can think of distributions as a set of instructions for a machine that generates random numbers. Let's say it generates the numbers of leaves on a tree. You may be wondering why we have a tree leaf number generating machine. The idea here here is that everything can generate data. It's not just mechanical stuff. It's leaves and animals and even people. The distribution is what specifies how the knobs and dials on our machine are set. Once the machine is set, every time there's a new tree, the machine pops out a random number of leaves from the distribution. It won't be the same number each time though. That's because it's a random selection based on the information the knobs and dials tell us about our distribution of leaves. When we look at samples of data generated by our leaf machine, we're trying to guess the shape of the distribution and how that machine's knobs and dials are set. But remember, samples of data are not all the data. So when we compare the shapes of two samples of data, we're really asking whether the same distribution, these machine settings, could have produced these two different but sort of similar shapes. If you got an especially expensive electricity bill last month, you might want to look at the histogram of your average daily energy consumption this month and the same month last year. Check them out side by side. It's not that realistic to expect that you consumed energy at exactly the same rate this month as you did the year before. There are probably going to be some differences. But your question is whether there's enough difference to conclude that your energy consuming behaviors have changed. When we think about data samples as being just some of the data made using a certain distribution shape, it helps us compare samples in a more meaningful way. Because we know that the samples approximate some theoretical shape, we can draw connections between the sample and the theoretical machine that generated it, which is what we really care about. Well, data come in all sorts of shapes. Let's take a look at a few of the most common, starting with the normal distribution. We mentioned the normal distribution when we talked about the different ways to measure the center of data, since the mean, median, and mode of a normal
Listen, if you're some data out here, you don't have to be normal, okay? Like, no matter what anyone tells you, frankly, just rude. So I just want to let you know that you are cared for and appreciated, data, and don't let anyone make you think that you have to be normal. You can be skewed if you want.
distribution are the same. This tells
Whoa, 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 whoa. My thingy's not picking up. Hold on. Been getting real uppity lately, huh?
us that the distribution is symmetric, meaning you could
Also, at some point, I realize my voice is not quite synced up. I haven't done a whole lot of testing today. At some point, I had this fixed, but not today. So that's a thing. But who cares? We're gonna just keep going.
fold it in half, and those halves would be the same, and then it's unimodal, meaning there's only one peak. The shape of a normal distribution is set by two familiar statistics, the mean and the standard deviation. The mean tells us where the center of the distribution is. The standard deviation tells us how thin or squished the normal distribution is. Since the standard deviation is the average distance between any point and the mean, the smaller it is, the closer all the data will be to the mean. We'll have a skinnier normal distribution. Most of the data in the normal distribution, about 68%, is within one standard deviation of the mean on either side. Just like the quartiles in a box plot, the smaller the range that 68% of the data has to occupy, the more squished it gets. Speaking of box plots, here's what the box plot for normally distributed data looks like. The two halves of our box are exactly the same because the normal distribution is symmetric. You've probably seen the normal distribution in a lot of different places. It gets called a bell curve sometimes. Attributes like IQ and the amount of Fruit Loops you get in a box are approximately normally distributed. Normal distributions come up a lot when we look at groups of things, like the total value rolled after 10 dice rolls or birth weights. We'll talk more about why the normal normal distribution is so useful in the future. As we've seen in this series, data isn't always normal or symmetric. Oftentimes, it has some extreme values on one side, making it a little bit skewed. Age at death during the Middle Ages is less skewed, because lots of people died young, while the time it takes to fill out the Nerdfighteria survey was right skewed, because some people lollygagged. In a box plot of data from a skewed distribution, the median will not usually split the box into two even pieces. Instead, the side with the skewed tail will tend to be stretched out, and often we'll see a lot of outliers on that side, just like the box plot of the Nerdfighteria survey times. When we see those features in our sample of data, it suggests that the distribution that generated our data also has some kind of skewed tail. Skew can be a useful way to compare data. For example, teachers often look at the distribution of scores on a test to see how difficult the test was. Really hard tests tend to generate skewed scores, with most students doing pretty poorly and a few who still ace it. Say we flash pictures of 20 Pokemon and ask people to name them. Here are their grades. Or another sample from a test asking people to list all 195 countries. We can compare the shapes and centers of these two groups of tests, as well as any other notable features. First of all, these two samples look pretty similar. Both have a right skew, both have a pretty low center, but the second test has a more extreme skew. Bigger skewed tails usually mean that the data, and therefore the distribution, has both a larger range and a bigger standard deviation than data with a smaller tail. The standard deviation is higher because not only are extreme data further away from the mean, they drag the mean toward them, making most of the other points just a little further from the mean too. While the direction of the skew tells you where most of the data is, always on the opposite side of the skewed tail, the extremeness of the skew can help you mentally compare the approximate measures of spread, like range and standard deviation. But we compare the shapes of two samples in order to ask whether the shape of the distributions that generated them are different, or whether one shape could have randomly created both samples. In terms of our machine analogy, we ask whether one machine with its knob settings could have spit out two sets of scores, one that looks like test A and one that looks like test B. Answering that question gets complicated, but we'll get there. Now that we've examined the tails, let's look at the middle of some distributions. Almost all the distributions we've seen so far are unimodal. They have only one peak, but there are many times when data might have two or more peaks. We call it bimodal or multimodal data, and it looks like the back of a camel, or maybe like two of our unimodal distributions pasted side by side. And that's probably what's happening, the unimodal stuff, not the camel thing. Often when you see multimodal data in the world, it's because there are two different machines with two different distributions that are both generating data that's being, for some reason or another, measured together. One possible example of this is the length in minutes that the geyser Old Faithful erupts. Most eruptions last either about 2 minutes or about 4 minutes, with few eruptions around the 3-minute mark, giving us a bimodal distribution. It's entirely possible that there are two different mechanisms behind the data, even though they're being measured together. For example, one set of conditions may lead to an eruption that's about 2 minutes long, and another, maybe a different temperature or latency, leads to a different kind of eruption, which lasts on average 4 minutes. Since these two potentially different types of eruptions are being measured together, the data looks like they come from one distribution with two bumps, but it's likely there's two unimodal distributions being measured at the same time. Another example that you don't need to be a geologist to understand is the race times for some marathons. While this data may look like it comes from a unimodal distribution, in reality there are two big groups of people who run a marathon. Those who are competing, and those that do it to prove they can do it. There's usually one peak around the time that all the professional runners cross the finish line, and another when the amateurs do. While we don't know for sure that bimodal data is secretly two distributions disguised as one, it's a good reason to look at things more closely. We'll finish today with uniform distribution. Even though we haven't mentioned uniform distributions yet, you've probably come across them in your everyday life. Each value in a uniform distribution has the same frequency, just like each number on a die has exactly the same chance of being rolled. When you need to decide something fairly, like which of your 6 roommates has to do dishes tonight or which friend to take to the Jay-Z concert, the best thing you can do is use something like a die that has a uniform distribution. That gives everyone an equal chance of being picked. And you can have uniform distributions with any number of outcomes. They're a 20-sided die. When you're in Vegas playing a round of roulette, the ball is equally likely to land in any of 38 slots. There's a difference between a shape of all the data and the shape of a sample of the data. When we talk about uniform distribution, we're talking about the settings of the data generating machine. It doesn't mean that every sample, or even most samples of our data,
distribution. Some mechanism of chance that has an equal, not a skewed, probability of occurring? I guess that's what that'll be.
It will have exactly the same frequency for each outcome. It's entirely possible that rolling a die 60 times results in a sample shape like this, even if we know the theoretical distribution looks like this. Using statistics allows us to take the shape of samples that has some randomness and uncertainty and make a guess about the true distribution that created that sample of data. Statistics is all about making decisions when we're not sure. It allows us to look at the shape of 60 dice rolls and figure out whether we believe the die is fair, or whether the die is loaded, or whether we need to keep rolling. Whether it's finding the true distribution of eruption times at Old Faithful, or showing evidence that a company is discriminating based on age, gender, or race, the shape of data gives us a glimpse into the true nature of what's happening in the world. Thanks for watching, and DFTBA Q. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Imigholt studio in Indianapolis, Indiana, and it's made...
I need more coffee. I'll be back. Give me like... I don't know. Give me like 5 minutes to put some coffee on. I'll be right back. Super exciting stuff, I know. Listen, relax. Don't be so judgmental, okay? Boop. Boop. Do you like how I just left you in blackness, in darkness, just to make you stronger? Don't forget I did this for your own good. Boop, boop. Okay, on to the next one. My coffee is brewing. Life is good.
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. Today we're talking about relationships. No, not why your cat just doesn't seem to like you. We're talking about data relationships, like how you can use one variable to predict another. Like if you can predict whether or not people who write in all capital letters are more likely to default on loans, whether people drive faster after they watch Fast and Furious movies, or whether people blink more often when they're lying. We'll start with the simplest data relationship, one between two continuous variables, also called bivariate data. But first, we're going to need to visualize our data using a scatter plot. The scatter plot has been called the most versatile, polymorphic, and generally useful invention in the history of statistical graphics.
Really?
Impressive. And as such, they're pretty much everywhere, including on your favorite news site. News outlets now have data journalists on staff to visualize and make sense of data. To make a scatter plot of Old Faithful eruption duration and latency, which is the time between eruptions, we put one variable on the x-axis and the other on the y-axis. Then each data point is placed so that it's in line with both its eruption duration and its latency. Now we can start to see a relationship. There are clusters, two blobby-looking groups of points, which supports our guess there are likely two kinds of eruptions, one with a longer buildup and a longer duration, and one with a shorter buildup and shorter duration. Just like the histogram and dot plot, a scatter plot allows us to see the shape and spread of data, but now in two dimensions. This data is clustered, but scatter plots are useful for identifying all kinds of relationships, both linear and nonlinear. For now, let's focus on linear relationships with a classic example, the relationship between the heights of fathers and sons. It makes sense that a tall father would produce a tall son, but we can do better than just a hand-wavy statement. In 1903, the statistician Carl Pearson published an influential paper in his own journal, Biometrica. One section of the paper describes the relationship between the heights of dads and their male children. In this paper, Pearson fit a line through the data to describe the relationship rather than just relying on his eyes to see a pattern. The line, called a regression line, is the line as close as possible to all the points at the same time. And note here, Pearson used
So I knew that, but also I didn't know it was such a simple definition. We're gonna just write that in. So a regression line is the line that is as close as possible to all the dots.
used feet and inches in his paper, so we will too. Lines are a great way to describe a relationship because they have a nice formula. Y equals mx plus b, just like you learned in algebra. The m, or slope, tells you a lot about your data. It tells you that an increase of 1 inch of a father's height leads to an increase of m in the son's height, about half an inch in Pearson's paper. So on average, dads who are 6'1" have sons that are about half an inch taller than the sons of fathers who are 6 feet tall. That allowed Pearson to make a prediction about the height of the son from the height of the father. And this is why these lines are so useful. They allow us to pretty accurately predict one variable based on the value of another. The relationship between car weight and gas efficiency allows us to be pretty sure a smart car gets better mileage than a Hummer. One note of caution here, the slope relies heavily on the units of x and y, since it's a measure of how many units y increases with each increase of 1 unit in x. If I decided to measure the sun's height in meters, the m, or slope, will change, even though the relationship didn't. When we see a non-zero slope, also called a regression coefficient, it's a sign that there
A regression coefficient is a non-zero slope.
there's some kind of relationship between our two variables, but that's pretty much all it tells us. We don't know how strong that relationship is. For more information, we need to look at correlation. Correlation measures the way two variables move together, both the direction and closeness of their movement.
Correlation measures the closeness, the way two variables move together, both in direction and closeness of their movement.
You may have read articles that claim there's a positive correlation between exercise and heart health. That just means if you exercise more, your heart tends to be healthier. A positive correlation looks something like this on a scatter plot, while a negative one, like the correlation between the number of cigarettes smoked each day and lung health, might look like this. Higher values of cigarettes smoked tend to have lower values for lung health. We now know what correlations look like in general, but to understand them more deeply, we're going to take a closer look. If two variables have a positive correlation, they move in the same direction. We can see this in our scatter plot if we draw two lines across the graph, one at the mean of each of our variables, to divide the plot into 4 quadrants. When two values are positively correlated, like how many miles you run and the number of calories you burn, most of the points will be in the upper right and lower left quadrants. In these quadrants, the values for miles and calories burned are either both large or both small. The more miles you run, the more calories you burn. The opposite happens when the correlation is negative, like the relationship between vaccination rates and rates of preventable illnesses. Instead of moving together, the variables move in the opposite direction. So the points are mostly in the upper left and lower right quadrants, where either vaccination rate is small and rate of illness is large, or vice versa. Since vaccination rate and rate of preventable illness have a negative correlation, as vaccination rates increase, rates of preventable illness decrease. The more closely two variables move together, the stronger the relationship will be, positive or negative. If the points are in all of the quadrants pretty evenly, you just have a blob or a cloud. You don't have a strong relationship. As I mentioned before, the units of your variables can affect the regression coefficient and can also affect the calculation of our correlation. To get around that, we use the standard deviations to scale our correlation so that it's always between -1 and 1.
Okay. I need to hear that again. Okay, so she says, as I mentioned before, the units of your variables can affect the regression coefficient. The regression coefficient is the non-zero slope.
And can also affect the calculation of our correlation. To get around that, we use...
Okay, so in order to have a consistent I always forget, calculation, we use the standard deviation. And if we remember, the standard deviation is also called the average difference of how far a point deviates from a norm on average, right? So we use standard deviation to scale our correlation so that it is always between -1 and 1. This is our correlation. Love my spelling. Coefficient. Otherwise known as R.
The standard deviations to scale our correlation so that it's always between -1 and 1. This is our correlation coefficient, R. Interpreting R involves two things: the sign of the number, that is whether it's positive or negative, and how big the number is.
Okay, So R is the correlation coefficient, which is the scaled correlation. This correlation that is scaled between -1 and 1.
The sign will tell you whether your two variables move together, positive R, or in opposite directions, negative R. A correlation of 1 or -1 would be a perfectly straight line, meaning you can exactly predict one value from the other. Say we looked at correlation of the number of hours you're asleep versus awake. If I know one of those values, I can tell you exactly what the other one is. We all only have 24 hours in a day. Even Beyonce. As you get closer and closer to a correlation of 0, the points are more and more spread out around our regression line. And eventually, at 0, there's no linear relationship at all. It's just dots. When you look at a scatter plot, remember that you can't deduce a correlation just by the steepness of the regression line. In our earlier father-son heights example, we changed our units to meters, and our line didn't look as steep, even though it's the same data. Data with steep lines can have low or high correlations. We also use the squared correlation coefficient, R squared. R squared is always between 0 and 1.
Squared correlation. R squared is always between 0 and 1, and it tells us in decimal form how much variance of one variable is predicted by another. Yo! Okay. I'm gonna go get some more coffee. Oh my goodness. We're gonna crush this. We're gonna destroy it. We're getting so smart. Our smartness is too smart. Boop. Boop. I have returned, fuel in hand and ready to get statistical. Boop. Boop. Boop.
And tells us in decimal form how much of the variance in one variable is predicted by the other. In other words, it tells us how well we can predict one variable if we know the other. While they won't usually give R squared an explicit mention, you'll see articles claim things like the ounces of soda a person drinks is highly predictive of weight, which means there's a large R squared. You can think of R squared as a measure of how accurate your guesses would be if you used your linear equation to predict one variable from another. If you had an R squared of 0.7 for the cigarettes and lung health data, that would mean that cigarette usage predicts 70% of the variation in how healthy our lungs are. You could pretty accurately predict someone's lung health if you knew how many cigarettes they smoked. An R squared of 1 means you can perfectly predict one variable from the other, since 100% of this variation is in one variable. This can seem pretty obvious when you think about conversion. Like temperature in Fahrenheit can be predicted by temperature in Celsius. In this case, we're not actually measuring the temperature in Fahrenheit, but it's being predicted by Celsius. So in general, the higher the R squared, the better the fit.
The higher the R squared, the better the fit.
Breaking news from City Hall today. The mayor has announced a plan to cut down on the number of people who drown every year. Sources close to the mayor tell us he's seen some very interesting correlations between drownings and air conditioning usage and drownings and Nicolas Cage movies, or as I like to call it, air cons and con airs. Both are highly correlated with drownings. Here's evidence. If we look at AC sales data over the past 10 years, and even more proof if we look at Nicolas Cage movies over the same time period, the Nick Cage data was provided to us by Tyler Vegan. So as of today, our mayor has enacted the Cool Cage Act, which will prohibit the sale of air conditioners and create a Nicolas Cage task force that will do everything to prevent Nicolas Cage from starring in any movies. The mayor assures us that because of the strong correlation she saw, as well as the strong will of our city, we will surely have next to no drownings this coming year. The Cool Cage Act may seem silly, but we're constantly flooded with messages that equate correlation and causation. And as you've heard before, correlation doesn't equal causation. Just because two variables are related doesn't mean that one variable causes the other. The examples the mayor uses are perfect examples of things that can go wrong when interpreting correlations. When one thing, A, is correlated with another, B, there are a few possible reasons. A causes B, B causes A. There is a third variable, C, that causes both A and B, even though A and B aren't related, or there's no relationship at all. It's just coincidence.
Pretty standard basic stuff, but we're gonna copy it down. A causes B, B, B causes A. There is a third variable that is affecting both, and it's a coincidence.
The correlation the mayor saw between air conditioning and drownings is probably caused by a third unmentioned variable, heat. When it's hot, people go buy more air conditioners and they go for a swim, leading to a correlation, even though there's no direct link between the two. And as for Nicolas Cage, he probably shouldn't feel too guilty about causing worldwide drownings. Sometimes two completely unrelated things are correlated just by random chance, with no causal link at all. These correlations get called spurious correlations, and they can be hard to catch. But
Also known as a spurious correlation.
when the correlation is between two very specific things, like Nicolas Cage movies and all drownings in 3 feet of water when a dog was present, we should be suspicious that someone tried every weird subset of data until they found a relationship. Before we finish with correlation, I just want to warn you, R and R squared aren't everything. It's important to look at a scatter plot of data when you can. These are the Datasaurus dozen. These very different plots all have the same correlation, but we can see that the relationships are completely different. Correlation is an important piece of the puzzle when you're looking for a linear relationship between two variables. It goes above and beyond the y equals mx plus b and gives us information about how well that line explains the data. Understanding the relationships between variables and events helps us predict what things are going to happen in the future, and also reflect on why things occurred in the past. A correlation can help you predict how much money you'll make after years of working your way up as a lemonade salesperson, or if watching that next Fast and Furious movie in the theater might encourage you to speed. According to an analysis by Harvard Medical School professor Anupam Jena, those two things could be related. Relationships are important, the human kind and the data kind. Correlation allows us to better understand relationships between data, and maybe also the data of our relationships. Maybe you can find correlations between the amount of time you spend at work or school and how much affection your cat shows you. Mr. Fluffy misses you. Thanks for watching. I'll see you next time. Crash Course Statistics.
Okay, we're gonna look up something else. We're gonna watch a different stats thingamajig, okay? Cause kinda getting sick of the format. Need some variation. Need some variance, right? So let's take a look. That Z statistics guy seem to have some decent content. We're gonna.
Hey team, Justin Zeltzer
Oh,
here
whoa!
from Z.
Chill, bro. Chill. All right, let's see what we got. What do you think, guys? These are the playlists. I think I'm going to do. Descriptive statistics, because that's just vibe-wise, it's a little boring, more boring. So I'd like to get it out of the way if we're gonna cover this series. Let's watch a little of this.
Hey team, and welcome to the first video in a series on descriptive statistics. My name is Justin Zeltzer, and over the next 12 or so videos, I'll be leading you through every descriptive measure you're ever likely to need. This first video is going to focus on the mean, but you'll find the rest of the series up on zstatistics.com. Now, even though these videos are aimed at beginners, I'd say even statistical veterans will learn something new in each of them, as I approach things in an intuitive way and have tried to kind of go beyond the boring definitions of things. Well, let's not waste your time. Let's get stuck straight into it, shall we? Now, the word mean comes from the French mean, from around the 1300s.
Oh, see, that's something.
And originally
new.
was meant to mean the middle of two musical notes. Now, when we're finding the mean from a population, we give it the symbol, the Greek symbol, mu. And to calculate the mean, we do the sum of all the observations. This Greek letter sigma here indicates we are to sum all of the x values. So it's the sum of x over the total number of observations, n, which is fairly intuitive. Now, if you're taking the mean from a sample, nothing much happens to that formula, except that we use a lowercase n to represent the number of observations instead of that uppercase n for the population. We're not going to get too bogged down into populations versus samples in this little video, but if your curiosity gets the better of you, I'll put up a little link here for a video I did on this exact topic. So let's have a look at the mean in action. If you're trying to find the mean of the following sample, 10, 28, 28, 33, and 54, it's as simple as adding them up and dividing by 5, because of course there are 5 observations. Now this is very straightforward, and I imagine most of you would have no problem in carrying out that sum. Turns out it's 30.6, so we'd say that the mean of this sample here is 30.6. Now, as a bit of a convention, you often provide the mean to one more decimal place than the original dataset was given in. So here, because the original dataset was given to no decimal places, I'm providing the mean to one decimal place. Again, that's just a convention, but it seems to be followed by most textbooks and journals and statistical thinkers alike. So good to start getting into some nice statistical habits here, eh? But it's as simple as that.
Okay, so this is important. Convention alert. When taking the mean of data with no decimal points, it is conventional to write the answer to one decimal point, e.g. 1.1.
Now for the advanced section of this video, I've got 3 little extra pieces we're going to have a look at. Firstly, I'll try my hand at calculating a weighted mean. I'll then look at a special case where we try to find the mean of a categorical variable. And finally, I'll offer you a challenge question, which I'll ask you to answer for me in the comments of this video. Or at least you can big up anyone that's got in there before you with the correct answer. So to introduce this, let's take another look at the sample we just used. So there's our 10, 28, 28, 33 and 54. Another way of describing this data set is to put it into a table form like this, where I've got x in one column. These are all our values of our variable x. That's 10, 28, 33 and 54. And then I provide f of x, or in this case we can say the frequency of x, in this second column. So that's 1, 2, 1 and 1. And notice that of course the sum of all these frequencies is going to equal 5, the number of observations. So the reason why I'm showing you both of these side by side is to get across the idea that the weighted mean is so intuitive and you almost don't need a formula for it. If you've watched any of my videos before, you'll know how reticent I am to just provide a formula and say, just use that. It's not really my way. I like to make things intuitive, so let me have a go at doing this. In the initial example, what we did was we summed up all the observations and divided by 5. But of course, you can probably recognize that 2 of these values are 28. So without even worrying about what a weighted mean is, we could have known to just, well, let's times 28 by 2 and then add it to all the other numbers. Doesn't really change anything, does it? But in writing it like that, you can see that we've effectively, on the numerator here, weighted each of the observations by the frequency that they occur. So 10 is multiplied by 1 because there's only one 10. 28 is multiplied by 2. 33 is multiplied by 1, etc. And then we divide by the total number of observations, or alternatively you can consider that the total number of weights. So in other words, if you were to see a formula that looks like this, yeah, that looks pretty ugly, but it should be quite intuitive, right? You're multiplying all the values of x by their frequencies and summing them up, and then dividing by the sum of all the frequencies. So it's quite literally what we are doing in this formula above here. I guess I wanted to show it to you this way, because I wanted you to appreciate that a weighted mean is actually nothing special. At the end of the day, a regular mean is just a weighted mean where all the weights are 1, right? So a weighted mean's really no different, just as a fancy formula. Now, as promised,
Okay, that seems important to know. So, a weighted mean is a mean that is written formulaically, such that repeated data points are timesed by how much they are repeated. The minute is the number of weights, or just how many data points there would be if they were all weighted by 1. Wow, I'm a genius. Look at me writing stuff down that someone else has said. Okay, I mean, yeah, that makes sense. Weighted mean, it's just a different convention, I guess. So there's probably some benefits to doing it that way in terms of like making formulas more concise. I get it, I get it, I get it. Okay.
Let's have a look and see if we can find the mean of a categorical data set. So here we have one that I've created, which is just male or female. Let's just say this is a litter of dogs. And we want to find the mean sex of the dogs. Is that even a question you can ask? Doesn't sound right, does it? But is it possible to find the mean of this data set?
They're probably like
Well,
4
not
F
as
and
written,
2
but
F.
say we define all the females as ones and all the males as zeros, we now have a numerical data set for which we can find the mean. So again, that's quite straightforward. I just add up all of those values and divide by 6 in this case. It looks like there are 4 females and 2 males. So this calculation becomes 4 on 6, or 0.66666666. Now what do you think that represents? Well, in this case, because it's a binary variable, that's a categorical variable with just 2 options, the mean is actually the proportion of the category that we defined as 1. So this represents the proportion of females in this litter of dogs, if you like. So a mean of a binary variable actually gives you the proportion.
The mean of the of a binary variable gives you the proportion.
Now, I wouldn't get too much cuter than that. I wouldn't try to apply a mean to a categorical variable with more than 2 values. It certainly wouldn't make sense in that case. But in the binary case, it certainly does. Okay, so are you ready for your challenge question? Here we go. Calculate Georgia's weighted average mark that she's got from her statistics degree thus far. She's done 4 subjects, and here are her marks.
Yeah.
And these are the credit points that...
We're not doing that. Instead, it's story time. And by story time, I mean dry writing time. And by dry writing time, what I mean is we are going to read about the philosophy of statistics on one of my favorite websites, the Stanford Encyclopedia of Philosophy. Yeah, it's good stuff. So, are we ready, kids? Are we ready to dig into this material and enjoy a little pleasant reading? Yeah? All right. Let's get into it. It's 9:08. Okay. Statistics investigates and develops specific methods for evaluating hypotheses in the light of empirical facts. A method is called statistical, and thus the subject of study in statistics, if it relates facts and hypotheses of a particular kind. The empirical facts must be codified and structured into data sets, and the hypotheses must be formulated in terms of probability distributions over data sets. The philosophy of statistics concerns the foundations and the proper interpretation of statistical methods, their input, and their results. Since statistics is relied upon in almost every empirical scientific research, serving to support and communicate scientific findings, the philosophy of statistics is of key importance to the philosophy of science. It has an impact on the philosophical appraisal of scientific method and on the debate over the epistemic and ontological status of scientific theory. The philosophy of statistics harbors a large variety of topics and debates. Central to these is the problem of induction, which concerns the justification of inference or procedures that extrapolate from data to predictions and general facts. Further debates concern the interpretation of the probabilities that are used in statistics and the wider theoretical framework that may ground and justify the correctness of statistical methods. A general introduction to these themes is given in sections 1 to sections 3 and 4 provide an account of how these themes play out in the two major theories of statistical method, classical and Bayesian statistics, respectively. Section 5 directs attention to the notion of a statistical model, covering model selection and simplicity, but also discusses statistical techniques that do not rely on statistical models. Section 6 briefly mentions relations between the philosophy of statistics and several other themes from philosophy of science, including confirmation theory, evidence, causality, measurement, and scientific methodology in general. So I don't know how many of these I'm going to read through today, but let's try and get through maybe 1 and 2. And then we'll come back and do more later. Statistics and Induction, Section 1. Statistics is a mathematical and conceptual discipline that focuses on the relation between data and hypothesis. The data are recordings of observations or events in a scientific study, e.g., a set of measurements of individuals from a population. The data actually obtained are variously called the sample data, or simply the data, and all possible samples from a study are collected in what is called a sample space. The hypothesis, in turn, are general statements about the target system of the scientific study, e.g., expressing some general facts about all individuals in the population. A statistical hypothesis is a general statement that can be expressed by a probability distribution over sample space, i.e., it determines a probability for each of the possible samples. Statistical methods provide the mathematical and conceptual means to evaluate statistical hypotheses in the light of a sample. To this end, the method employ probability theory and, incidentally, generalizations thereof. The evaluations may determine how believable a hypothesis is, whether we may rely on the hypothesis in our decisions, how strong the support is that sample gives to the hypothesis, and so on. Good introductions to statistics abound. To set the stage, an example, taken from Fisher, 1935, will be helpful. The tea-tasting lady. Consider a lady who claims that she can, by taste, determine the order in which milk tea were poured into the cup. Now imagine that we prepare 5 cups of tea for her, tossing a fair coin to determine the order of milk and tea in each cup. We ask her to pronounce the order, and we find that she is correct in all cases. Now, if she is guessing the order blindly, then, owing to the random way we prepare the cups, she will answer correctly 50% of the time. This is our statistical hypothesis, referred to as the null hypothesis. It gives a probability of 1/2 to a correct guess, and hence a probability of 1/2 to an incorrect one. The sample space consists of all strings of answers the lady might give, i.e., all series of correct and incorrect guesses. But our actual data sits in a rather special corner in this space. On the assumption of our statistical hypothesis, the probability of the recorded event is a mere 3%, or 1/2 to the 5th. More precisely, on this ground, we may decide to reject the hypothesis that the lady is guessing. According to the so-called null hypothesis test, such a decision is warranted if the data actually obtained are included in a particular region within the sample space, whose total probability does not exceed some specified limit, standardly set at 5%. Now consider what is achieved by the statistical test just outlined. We started with a hypothesis on the actual tea tasting abilities of the lady, namely that she did not have any. On the assumption of this hypothesis, the sample data we obtained turned out to be surprising, or more precisely, highly improbable. We therefore decided that the hypothesis that the lady has no tea tasting ability whatsoever can be rejected. The sample points us to a negative but general conclusion about what the lady can or cannot do. The basic pattern of a statistical analysis is thus familiar from inductive inference. We input the data obtained thus far, and the statistical procedure outputs a verdict or evaluation that transcends the data, i.e., a statement that is not entailed by the data alone, if the data are indeed considered to be the only input, and if the statistical procedure is understood as an inference. Then statistics is concerned with ampliative inference. Roughly speaking, we get out more than we have put in. And since the ampliative inference of statistics pertains to future or general states of affairs, they are inductive. However, the association of statistics with ampliative and inductive inference is contested both because statistics is considered to be non-inferential by some and non-ampliative by others. Okay. Despite such, so I was just looking at ampliative because I've never seen that word applied in this context, or really at all, I don't think. So it's like amplify, right? Ampliative, we get out more than what we put in. That tracks. Just saying. Okay. Despite such disagreements, it is insightful to view statistics as a response to the problem of induction. Interesting. House in 2000 and the entry of the problem of induction. This problem, first discussed by Hume in his Treatise of Human Nature, but prefigured already by ancient skeptics like Sextus Empiricus, is that there is no proper justification for inferences that run from given experience to expectation about the future. Transposed to the context of statistics, it reads that there is no proper justification for procedures that take data as inputs and that return a verdict, an evaluation, or some other piece of advice that pertains to the future or to general states of affairs. Arguably, much of the philosophy of statistics is about coping with this challenge. By providing a foundation of the procedures that statistics offers, or else by reinterpreting what statistics delivers so as to evade the challenge. It is debatable that philosophers of statistics are ultimately concerned with the delicate, even ethereal issue of the justification of induction. In fact, many philosophers and scientists accept the fallibility of statistics and find it more important that statistical methods are understood and applied correctly. As is so often the case, the fundamental philosophical problem serves as a catalyst. The problem of induction guides our investigations into the workings, the correctness, and the condition of applicability of statistical methods. The philosophy of statistics, understood as the general header under which these investigations are carried out, is thus not concerned with ephemeral issues, but presents a vital and concrete contribution to the philosophy of science and to science itself. All right, that was part 1. We are going to move on to part 2. I'm just going to, I'm not going to be reading all that mathities, all those little mathy formulas. Frankly, because my mathematical knowledge is very limited and I don't know what the words are to read out certain mathematical things. So I'm going to read it, but then we're going to skip. We're going to skip all the mathy parts that I can't, that I don't know how to read out in my head. Part 2, Foundations and Interpretations. While there is large variation in how statistical procedures and inferences are organized, they all agree on the use of modern measure theoretic probability theory, or a near kin, as the means of express hypothesis and relate them to data. By itself, a probability function is simply a particular kind of mathematical function used to express the measure of a set. Let W be a set with elements S and consider an initial collection of subsets of W, e.g. the singleton sets S. Okay, this set theory, basic set theory, like I get the broad strokes, right? It's just like you have some stuff and you put the stuff in it and that's the set, right? Now consider the operation of taking the complement R something of a given set R. The complement R little dashy line contains exactly and all those S that are not included in R. Next, consider the join R and Q. I think it's and, might be R. Give sets R and Q. Yeah, R and Q. An element S is a member of R and Q precisely when it is a member of R, Q, or both. Is that or then? The collection of sets generated by the operation of complement and join is called an algebra. The collection of sets generated by the operation of complement and join is called an algebra, denoted S. In statistics, we interpret S as the set of samples, and we can associate sets R with specific events or observations. A specific sample S, lowercase s, includes a record of the event denoted with R, exactly when S sum R, that is sum, right? We take the algebra of sets like R as a language for making claims about the samples. A probability function is defined as an additive normalized measure over the algebra, a function. And this is where they lose me. Whenever P of R is greater than 0, I assume P means probability, it determines the relative size of the Q within the set. R. It is often read as the probability of the event Q given that the event R occurs. Okay, that helps. It is often read as the probability of the event Q given that the event R occurs. Recall that the set R consists of all samples S that include a record of the event associated with R. By looking at P of Q or R, we zoom in on the probability function within this set R, i.e. we consider the condition that the associated event occurs. Now, what does the probability function mean? The mathematical notion of probability does not provide an answer. The function P may be interpreted as 1. Physical, namely the frequency of the propensity of the occurrence of a state of affairs, often referred to as the chance, or else as 2. Epistemic, namely the degree of belief in the occurrence of the state of affairs, the willingness to act on its assumption, a degree of support or confirmation or similar. This distinction should not be confused with that between objective and subjective probability. Both physical and epistemic probability can be given an objective and subjective character in the sense that both can be taken as dependent or independent of a knowing subject and her conceptual apparatus. For more details on the interpretation of probability, the reader is invited to consult Galavati, Gillies, Malor, von Plato, the Anthology of Eagle, the Handbook of Hayek and Hitchcock forthcoming, or indeed the entry on interpretations of probability. In this context, the key point is that the interpretation can all be connected to foundational programs for statistical procedures. Although the match is not exact, the two major types specified above can be associated with two major theories of statistics, classical and Bayesian statistics respectively. Alright, so classical statistics relates to physical interpretation of probability, and Bayesian statistics refers to epistemic interpretation of probability. Okay, cool, groovy. And the main difference between the two is one is making a statement that something is going to occur, and the other is making a statement that we believe that something is going to occur. All right, Groovy. I don't think I fully grasp that, but I'm caffeinated and we're gonna keep plowing. Keep plowing through the information here. Physical probability and classical statistics. In the sciences, the idea that probabilities express physical states of affairs, often called chances or stochastic processes, is most prominent. They are relative frequencies in series of events, or alternatively, they are tendencies or propensities in the system that realize those events. More precisely, the probability attached to the property of an event type can be understood as the frequency or tendency with which that property manifests in a series of events of that type. For instance, the probability of a coin landing heads is a half exactly when in a series of similar coin tosses the coin lands heads half the time. Or alternatively, the probability is half if there is an even tendency towards both possible outcomes in the setup of the coin tossing. The mathematician Venn and scientists like Quetelet and Maxwell are early proponents of this way of viewing probability. Philosophical theories of propensities were first coined by Peirce, 1910, and developed by Popper, 1959, Mellor, 1971, Bigelow, 1977, Gear, 1976. See Hanfield for a recent overview, 2012. A rigorous theory of probability as frequency was first devised by von Mises in 1981, also defended by Reichenbach 1938, and beautifully expounded in von Lamboggen in 1987. They mean 1980. I think they meant 1983 here, because I don't know how Reichenbach could have defended this in 1938 when this was written in 1981. Just saying. I think that's a little bit of a typo going on there. The notion of physical probability is connected to one of the major theories of statistical methods, which has come to be called classical statistics. It was developed roughly in the first half of the 20th century, mostly by mathematicians and working scientists like Fisher, Wald, Neyman, and Pearson, and refined by very many classical statisticians of the last decade. The key characteristic of this theory of statistics aligns naturally with viewing probabilities as physical chances, hence pertaining to observable and repeatable events. Physical probability cannot meaningfully be attributed to statistical hypotheses, since hypotheses do not have tendencies or frequencies with which they come about. They are categorically true or false once and for all. Attributing probability to a hypothesis seems to entail that the probability is read epistemically. Classical statistics is often called frequentist, owing to the centrality of frequencies of events in classical procedures and the prominence of the frequentist interpretation of probability developed by von Mises. In this interpretation, chances are frequencies or proportions in a class of similar events or items. They are best thought of as analogous to other physical quantities, like mass and energy. It deserves emphasis that frequencies are thus conceptually prior to chance. In propensity theory, the probability of an individual event or item is viewed as a tendency in nature, so that the frequencies of the proportion in a class of similar events or items manifest as a consequence of the law of large numbers. In the frequentist theory, by contrast, the proportions laid down indeed define what the chances are. This leads to a central problem for frequentist probability, the so-called reference class problem. It is not clear what class to associate with an individual event or item. One may argue that the class needs to be as narrow as it can be, but in the extreme case of a singleton class of event, the chance of a course trivialized to 0 or 1, Since classical statistics employs non-trivial probabilities that attach to the single case in its procedures, a fully frequentist understanding of statistics is arguably in need of a response to the reference class problem. To illustrate physical probability, we briefly consider physical probability in the example of the tea-tasting lady. Physical probability. We denote the null hypothesis that the lady is merely guessing by H. Say that we follow the rule indicated in the example above. We reject this null hypothesis, i.e., denying that the lady is merely guessing, whenever the sample data S is included in a particular set of R possibilities. Set of R possible samples. So S sum R, and that R has a sum probability of 5% according to the null hypothesis. Now imagine that we are supposed to judge a whole population of tea-tasting ladies scattered in tea rooms throughout the country. Then by running the experiment and adopting the rule just cited, we know that we will falsely attribute special tea-tasting talents to 5% of those ladies for whom the null hypothesis is true, i.e., who are in fact merely guessing. In other words, this percentage pertains to the physical probability of a particular set of events, which by the rule is connected to a particular error in our judgment. Now say that we have found a lady for whom we reject the null hypothesis, i.e., a lady who passes the test. Does she have the tea-tasting ability or not? Unfortunately, this is not the sort of question that can be answered by the test at hand. A good answer would presumably involve the proportion of ladies who indeed have the special tea-tasting ability among those whose scores exceeded a certain threshold, i.e., those who answer correctly on all 5 cups. But this latter proportion, namely of ladies for whom the null hypothesis is false among all those ladies who pass the test, differs from the proportion of ladies who pass the test among those ladies for whom it is false. It will depend on the proportion of ladies who have the ability in the population under scrutiny. The test, by contrast, only involves proportions within a group of ladies for whom the null hypothesis is true. We can only consider probabilities for particular events on the assumption that the events are distributed in a given way. Do I understand anything that I'm reading right now? If I'm being honest, not really. I understand some of it. But I'm just making mental notes. See, I'll be able to listen to this later. Just put on this is kind of like visual notes for me, right? So I'll be able to pop this stream on later and listen to it. So we're going to keep going and finish out this section. Then I want to cover a video that just came out by Vervaeke about transcendent naturalism, which admittedly I have some sympathies towards given my relationship to Vervaeke's work, but I'm always critical of people I approve of. So it's gonna be we're gonna dig in and see if there's any reasonable critique I can make. There is a little bit too much woo in it, which makes me feel uncomfortable, but that's not necessarily a reason for discounting the thing. But we're gonna just keep crushing it and finish up this article, section 2. Okay. Epistemic probability and statistical theory. There is an alternative way of viewing the probabilities that appear in statistical methods. They can be seen as expressions of epistemic attitudes. We are again facing several interrelated options. Very roughly speaking, epistemic probabilities can be doxastic, decision theoretic, or logical. I don't know what doxastic means. Of or relating to belief, denoting the branch of modal logic that studies the concept of belief. Belief related, decision theoretic, or logical. Got it. Types of epistemic probability. Probabilities may be taken to represent doxastic attitudes in the sense that they specify opinions about data and hypotheses of an idealized rational agent. The probability then expresses the strength of degree of belief, for instance, regarding the correctness of the next guess of the tea-tasting lady. They may also be taken as decision theoretic, i.e., as part of a more elaborate representation of the agent, which determines her disposition towards decisions and actions about the data and the hypothesis. Oftentimes, a decision theoretic representation involves doxastic attitudes alongside preferential and perhaps other ones. In that case, the probability may, for instance, express a willingness to bet on the lady being correct. Finally, the probabilities may be taken as logical. More precisely, a probabilistic model may be taken as a logic, i.e., a formal representation that fixes a normative ideal for certain reasoning. According to this latter option, probability values over data and hypotheses have a role that is comparable to the role of truth values in deductive logic. They serve to secure a notion of valid inference without carrying the suggestion that the numerical values refer to anything psychologically salient. The epistemic view on probability came into development in the 19th and first half of 20th century, first by the hand of De Morgan in 1847, Boole 1845, later by Keynes 1921, Ramsey 26, DeFenti 37, and by decision theorists, philosophers, and inductive logicians such as Carnap 50, Savage 62, Levy 80, and Jeffrey 92. Important proponents of these views in statistics were Jeffrey 61, Edward 72, Lindsay 65, Good 83, Jaynes 03, 2003, as well as very many Bayesian philosophers and statisticians of the last few decades, e.g. Goldstein, Keidenberger, David. All of these have a view that places probabilities somewhere in the realm of the epistemic rather than the physical, i.e., not as part of a model of the world, but rather as a means to model a representing system like the human mind. The above division is certainly not complete, and it is blurry at the edges. For one, the doxastic notion of probability has mostly been spelled out in a behaviorist manner, with the help of decision theory. Many have adopted so-called Dutch book arguments to make the degree of belief precise and to show that, I'm sorry, I'm just looking at my little screen here, just saying, okay, yeah, why is it being all flashy and annoying? Anyway, where was I? For one, the doxastic notion of probability has mostly been spelled out in a behaviorist manner with the help of blah 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 mathematical theory of probability. According to such arguments, the degree of belief in the occurrence of an event is given by the price of a betting contract that pays out one monetary unit of the event manifest. However, there are alternatives to this behaviorist take on probability as doxastic attitudes using accuracy or proximity to truth. Most of these are versions or extensions of the argument proposed by Finetti. Others have developed an axiomatic approach based on natural desiderata for degrees of belief. Furthermore, and as alluded to above, within the doxastic conceptions of probability, we can make a further subdivision into subjective and objective doxastic attitudes. The defining characteristic of an objective doxastic probability is that it is constrained by the demand that the beliefs are calibrated to some objective fact. Okay, that is really annoying. Well, I can only hope that that's not really coming through all flashy like that, because that is super annoying. But anyway, we're going to keep going through here. A subjective doxastic attitude, by contrast, is not constrained in such a way from a normative perspective. Agents are free to believe as they see fit as long as they comply to the probability axioms. Statistical theories. For present concerns, the important point is that each of these epistemic interpretations of the probability calculus comes with its own set of foundational... Oof. Oh, man. My whole setup is getting messed up. This is no bueno. Alright, hold on, guys. Okay. Just needed to do a little reboot. All right. Let's keep going here. For present concerns, the important point is that each of these epistemic interpretations of the probability calculus comes with its own set of foundational programs for statistics. On the whole, epistemic probability is most naturally associated with Bayesian statistics, the second major theory of statistical methods. The key characteristic of Bayesian statistics follows directly from the epistemic interpretation. Under this interpretation, it becomes possible to assign probability to a statistical hypothesis and to relate this probability understood as an expression of how strongly we believe the hypothesis to the probabilities of events. Bayesian statistics, okay, so wait, hold on, that seems very important. The key characteristic of Bayesian statistics flows directly from the epistemic interpretation. Under this interpretation, it becomes possible to assign probability to a statistical hypothesis, to assign probability to and to relate this probability understood as an expression of how strongly we to the probability. Bayesian statistics allows us to express how our epistemic attitudes towards a statistical hypothesis, be it logical, decision theoretic, or doxastic, changes under the impact of data. To illustrate the epistemic conception of probability in Bayesian statistics, we briefly return to the example of the tea-tasting lady. Epistemic probability. As before, we denote the null hypothesis that the lady is guessing randomly with H, so that the distribution pH gives a probability of 1/2 to any guess made by the lady. The alternative H prime is that the lady performs better than a fair coin. More precisely, we might stipulate that the distribution P of H prime gives a probability of 3/4 to a correct guess. At the outset, we might find it rather improbable that the tea-tasting lady has special tea-tasting abilities. To express this, we give the hypothesis of her having these abilities only half the probability of her not having the abilities. P of h prime equals 1/3 and ph equals 2/3. Now, leaving the mathematical details to section 4.1, after receiving the data that she guesses all 5 cups correctly, our new belief in the lady's special ability has more than reversed. We now think it roughly 4 times more probable that the lady has the special abilities than that she is merely a random guesser. The take-home message is that Bayesian method allows us to express our epistemic attitudes to statistical hypotheses in terms of a probability assignment, and that the data impact on these epistemic attitudes in a regulated fashion. It should be emphasized that Bayesian statistics is not the sole user of an epistemic notion of probability. Indeed, a frequentist understanding of probabilities assigned to a statistical hypothesis seems nonsensical. But it is perfectly possible to read the probabilities of events or elements in sample space as epistemic, quite independently of the statistical method that is being used. As further explained in the next section, several philosophical developments of classical statistics employ epistemic probability, most notably fiducial probability, likelihoodism, and evidential probability, or connect the procedure of classical statistics to inference and support in some other ways. In all these developments, probabilities and functions over sample space are read epistemically as expressions of strength of evidence, the degree of support, or similar. Okay, so we've read all of that. Have we understood it? Well, if I had to summarize it, and I'm just going to turn that off because apparently I don't know what's going on with my stuff, but it seems to be having an issue. Basically, there are 2 ways of thinking about statistics. There's the classical and the Bayesian, which roughly approximate to physical versus epistemic interpretations of probability, respectively. So they sort of just went into it. T-Lady seems to be basically to probability what, Socrates is a man is to, modus ponens, modus tonens, and other philosophical examples, right? Conventional, in other words. And that's lovely. That's just lovely. What else have I learned? There's a bunch of stuff I need to figure out. Like, I don't really have these ideas solidified in my mind in terms of like the difference. I'm kind of inclined towards Bayesianism insofar as it seems a lot more meta. It's acknowledging of an individual agent. That seems pretty cool. But yeah, I don't know. It seems a little over my head at the moment. But that's why we're doing this, guys. That's why we're doing it. We're gonna get better at it. We're gonna get better at it. You and me. Just you and me. Okay? You and me. Whatever you're doing in your day, just want to say thank you for joining me on this adventure. And if you are enjoying this content, please feel free to support the channel. Hit that like button, hit that subscribe button. I will find a way for you to give me money. I think currently my my bank account for this stuff is in purgatory, but we'll figure it out. You and me, we'll figure out a way. And if you enjoy this content, please feel free to donate whatever you have. Life savings, firstborn child, whatever works. Whatever works. Okay. So I'm just pulling up this video right here. We're gonna watch this video on transcendent naturalism. And I'm gonna give my critiques.
Welcome everyone to the Cognitive Science Show. This is a new series with my ongoing partner in crime about these Cognitive Science Show series, Greg Enriquez. This is a new series we're entitled Transcendent Naturalism. We're trying to bring about the most, I think this is the right word, satisfying consilience between science and spirituality that we think is possible and viable right now. So what we're going to do is, first of all, sort of talk a bit about why this is problematic. And then I'm going to do a review. I'm not going to do a complete representation of an argument I made recently at the conference that Greg organized, the Consilience Conference, where this was the core thing we were addressing, and give Greg a chance to interact with it a little bit more dialogically. And then that will lead into Greg bringing in work from his UTalk framework that will also, I no doubt, given our past history, converge and synthesize with what I present. And then we intend to have on a third person, not the same person each time, that will enter into this discussion about transcendent naturalism. So, why...
Let me, if I can just pop in here. So yeah, this is a super exciting series that we're about to embark on, I think. I mean, you know, what is the meaning in mental health crisis? What's the kairos of the moment that we find ourselves in? And, you know, it's been super cool to do the consciousness, the self, the transformation, psyche, pathology, well-being. But what's the ground of understanding of meaning making and what's right for this moment? And that's what this series really feels like it's about. So at that center, it's a deep epicenter, at least for me, in relationship to our journey together and where we are in general. So I just want to offer that. So I'm really looking forward to it.
Me too. Me too. I can't think of anybody I'd be...
Okay, real quick, I'm probably gonna have to stop around halfway through because I think I'm gonna have an appointment at 11 o'clock. So we're gonna watch a little bit of this and see where we get, and I'll offer a few critiques, and then we'll come back to it at a later date.
They're doing it with than you. So these are two topics, of course, that are very significant, at least in people's background, science, the scientific worldview. And for those of you who sort of might say, well, I sort of reject the scientific worldview, you have to understand the scientific worldview isn't just rejecting this or that claim from Darwin's theory of evolution. It's rejecting the entire framework of science and technology that is pervasive and insinuated its way into everybody's life and everybody's way of thinking in a deep way. This is not some criticism or accusation. This is an observation that I hope to make good on, and I'm sure Greg will help me on this. And then the idea is, nevertheless, spirituality, and of course we're going to have to talk about what does that mean, because originally it meant relating to spirits. And is that still something we can talk about? And the answer is going to be sort of yes, but not in the way we used to think of them, perhaps. This is all something that's in question to begin with. But whatever that term is supposed to broadly mean today, and it means a lot, but vaguely, because many people identify as spiritual but not religious, there's something of import to spirituality. And this has to do with issues around connectedness, a sense of being in touch with what really matters, what's really real, having a capacity to become wiser, overcome foolishness, self-deception, to go through a kind of growth that is not just a growth in one's acquisition of factual knowledge. There's a lot of different overlapping things. We don't need to get clear on that right now. I'm going to argue that one of the things that binds them together is a notion that when we mean the words, part of what we've always pointed to with the word spirit is a capacity for transcendence, a capacity that we can transcend ourselves in some manner that is very, very significant. Now, this is problematic to have these two right now, and I'll turn things over to Greg in a minute to bring out his very famous, and deservedly so, discussion about the Enlightenment gap. But we have to understand that for us, these two things are at best orthogonal in our culture, science and spirituality, and frequently they're regarded as antagonistic to each other. To be spiritual means you don't just, you sort of reject scientific materialism. It's not clear what that's pointing to, and equating science with materialism is part of the problem we're going to talk about. And if you're scientific and you're rigorous, you don't believe in any of that woo stuff. And, by and large, there's a lot of crap that goes under the name woo, but that doesn't mean that everything can be easily dismissed away. There are real issues that have to be discussed. And so for us, they have this very tenuous and at times tortured relationship. But if you go back far enough, pretty much before the scientific revolution, reason
Something's happening. Oh, I love when my stuff messes up.
in the Christian framework, the Christian
Love it. I just love it. Okay.
a Platonic framework, etc. And there are many people who are making that case and bringing it out again for us today. D.C. Schindler, Catherine Pickstock, a host of people are just doing amazing work.
It is a fascinating book,
Yeah.
Aspects of Truth. I just
Yeah.
finished it. It's
Yeah.
lovely.
So, yeah, I've reached out to Catherine, and hopefully I'll get a chance to go to Cambridge and talk to her directly.
Lovely.
She'll figure in some of the discussions we're going to have.
Definitely. The idea of conformity and being and knowing in right relation is certainly something that's going to pop up a number of different times in our conversation.
And the deep connections between rationality and ritual, which I think are
Yep.
also something that we're going to
Amen.
discuss. So, it's not necessarily the case that these two things have to have a problematic relationship to each other, but nowadays they do. And there's some important reasons for that. And I go over to them in some deep detail, maybe excruciatingly so, in Awakening from the Meaning Crisis. And Greg also details them quite well in his. I had your book here. Where did I put it? In his wonderful new book. Do you have it nearby, Greg, to hold up in a shamelessly self-promotional fashion?
It is. I can go get it. It's actually on my kitchen table.
Okay, where did I put it? I had it right here the other day. So, anyways, we'll get it and we'll show it. So, Greg, in his new book, has also detailed these. The main thing that prevents us from bringing the two together is a view of a way in which one is supposed to create one's worldview. So this is how you create your worldview, and this is the idea that you build your scientific worldview out of whatever the hard sciences, the core sciences, and I'll always mean by them physics, chemistry, and biology, and that you should not propose anything in your ontology. That's your theory of the structure of reality, the kind of entities that really exist. You should not propose anything in them that is not derivable from those sciences. And many people also join to that a reductionist idea that biology will ultimately be completely explained by chemistry, which will ultimately be completely explained by physics. And then the idea is that the only thing that everything should be derived from in our ontology is the very bottom level of our physics, and that's the only place that is really real. This is known by various names, but reductionism is the most common name. And so the idea is something like this. All that stuff about meaning and the experience of beauty and all of that, and this comes from the Cartesian divide, Galileo, Descartes, all of that is just subjective. That's not in the objective world. The objective world is the world given to us by the hard sciences, and probably all that's real about that world is the very bottom level of the sort of quantum mechanics. Although there's this nasty problem of the irreconcilability of quantum mechanics and relativity, which we keep getting promised is going to be solved, and it hasn't been solved for I think over 50 years now. And when you get a recurrent pattern of failed problem solutions, this is from the problem-solving literature, you should consider that you have a flawed presupposition that is shared by all your failed problem formulations that is presented.
Okay, so here's what I think. I think a lot of people who are critical of Vervaeke from the traditional view, traditional academic view, probably think he flirts a little too much with the woo stuff. And if I'm being honest, some of the new stuff with the courses does rub me the wrong way. But, like, I don't think we can just simply dismiss what he's talking about because he does rely on a fair amount of academic arguments. So, in order to contend with it, I mean, I have to become a better criticizer. And if I'm being honest, like, I find a lot of stuff compelling because Vervaeke is. He speaks to some of the things that I've gone through in my life in terms of weird meditative experiences, and in a way that is a little more thorough than your usual people who, what is it, the Mind and Life Institute or any organization that works heavily with Buddhists, which, I mean, he certainly does some work with Buddhism, but having been an ex-Buddhist myself, it just hits a lot of notches for me in particular. So I'm with him on this journey, but I'm also never not one to buy into anything fully. So I want to hear it out, and I want to see that I can make sure that I fully understand it before I critique it. And that's asking a lot of me because, we're still working on building that intellectual power, which I currently need a little more of, I think, to give this the critique that it's due.
Preventing you from solving the problem. Why did I bring that up? Because it's quite possible that that whole way of framing things, that we should only include in our ontology what is derivable from the hard sciences, and ultimately what is most real is what is given to us by our fundamental physics, and everything above that is epiphenomenal or illusory, is part of the problem that we're facing. So that sort of that great divide between the subjective and the objective, and there's no way they can possibly meet because they are defined completely antithetical to each other. There is no possible mediating term, at least in this view. So there's no way, and this has all kinds of problems for truth and knowledge and meaning and all kinds of stuff. And then all we have is an ontology is what is derivable from our hard sciences, and what is probably most real, given that view, is the bottom level, and everything else is somehow just not real in some very important sense. And that means everything you consider spiritual, the meaning, the beauty, the sense of self-transcendence, that's probably illusory. It's definitely subjective, and the only transcendence you're really ever talking about is a kind of psychological improvement. It's not saying anything important about epistemology, how you know things, or ontology, the nature or being of things. So that's the problem we're in. And the problem is we can't just sort of
Can I give it just a real quick?
Yeah. Sorry.
No. So just how do we embody this? So I'm with a young man who I know, and we're at a party, and he's gone to college. And I said, "Oh, what did you learn?" And he's like, "Actually, I learned them just a bunch of chemicals." Okay. So he has a physically reductive neuroscience class and sort of an analytic philosophy class that is very harsh on love and other kinds of concepts. And so the take-home message that he gets from going to college is that I'm just a bunch of chemicals. And I think that really just sort of captures just meaning, hey, I thought I cared about my job, and I thought I loved my girlfriend, and no, that's oxytocin, and we can.
Okay, so here's a thing that is worth considering. So there is something, for me, intuitively unsatisfying about the worldview they're describing, that they're criticizing, the Cartesian whatever. There is something that feels very alienating about that perspective. And I think typically the typical science perspective is that, well, like, it may be alienating, but it is what's true, and we need to accept the harsh truths of reality in order to deal with reality. And history of society, people falling for nonsense. Oh my goodness, everything is just breaking down. This is no bueno.
We were just
Okay. Okay, well that's back. And now probably need to get a better capture card. It's giving me a lot of issues. Okay. So yeah, basically the long and the short of it is there is something that feels unsatisfying about that worldview, and maybe we need to just be practical and understand it. But I think that we can still look at it and critique it, and there may still be an angle. And just because something, there's a counter argument to the idea that, like, for instance, we just need to be practical is not really a good argument, and something being unsatisfying is not really an argument. What we can do is we can say, maybe there is more to, like a deeper, more satisfying answer. Like maybe there's a way of viewing the world that is both satisfying and true. And it doesn't have to just be, well, you just have to accept the harsh realities of life, and this is, that we are in fact an alienated being. But like, I get it though. Like, we've believed a lot of nonsense over the course of human history. We still believe a lot of nonsense. So the hesitance to move to something that feels a little more wooey feels like we're heading towards dangerous territory where we're like letting more nonsense in when the other stuff has been working fine. And I understand that the only thing that's unsatisfying about that worldview seems to be that it caused people mental anguish to inhabit that worldview. And it seems like the only reason we're looking for a different perspective is to resolve that tension of the internal sense of emptiness that maybe a true thing causes, and maybe that's not a good enough reason to give up the so-called truths we've been finding. I'm not sure if any of that makes sense. I realize I'm speaking very generally. I'll have to get more specific and more concise about it, but these are just like the flow of words as they start coming out of my head. So we're gonna keep watching this. Got a few more minutes before my appointment, so let's continue to enjoy this.
It's basically an unfolding bumping of molecules or atoms or quarks, or I don't know why wherever you're going to stop. But it's this mechanistic billiard ball at some fundamental level of unfolding that really is determining everything, and you just live in an illusory epiphenomenal world. And if you say that to yourself, I mean, we talk about meaning in mental health crisis, and you're like, okay, well, now I'm going to get up and really take care of my kids because that really matters, right? If I'm just a bunch of chemicals. So anyway, I'll just sort of, at the embodied human level, that is real consequence. But that's essentially what it will manifest.
Right, and then what is on offer in popular culture as a response to that is a decadent romanticism where just trust your gut. Love is the most real thing, and this is asserted without any defense or argument. And then you have the severing, right, of any of these claims from any attempts to explain them in a rationally defensible manner. And then people careen and vacillate between those two, right? And that's because fundamentally what the Cartesian world gives us is an unstable notion of realness. Realness is what is objectively mathematically measurable, or that could all be a simulation. Think about how popular that notion is right now. That could all be a simulation, and all that's real is my subjective self-awareness, because that's the only thing that I directly... And then we vacillate between a solipsism and a soul-crushing, right, kind of positivism.
I frame the shorthand frame to the Enlightenment gap, which is the absence of a conciliant model that places mind and matter. Frame
solipsism, objective self-awareness, because that's the only thing that I directly... And then we vacillate between a solipsism and a soul-crushing, right, kind of positivism.
I frame the shorthand frame to the Enlightenment gap, which is the absence of a conciliant model that places mind and matter, science and subjective and intersubjective knowing, right relation, as between being stuck between the ontology of Newton, that's a mechanical billiard ball all the way down, and the epistemology of Kant, which is basically a trapped, potentially, depending on how you read Kant, a trapped phenomenological, quasi-solipsistic idealism, and how do those things go to you? Basically, what do you choose one or the other? Well, we certainly don't have a coherent, synthetic, obvious, shareable frame that appreciates the conformity of our epistemological structures on the ontological structures in which we're embedded, and I think that's what we're after here.
Yes. And so I think that was very well said, Craig. I like that. And Newton and Kant are playing off against each other and really profound, and Kant more playing off of Newton than Newton off of Kant. But nevertheless, yeah.
But it's important to understand, of course, what Galileo and Kant did relative to scholasticism and the Christian. You know, the heavens get collapsed, and then all of a sudden there's all these small laws. And by the way, the Newtonian metaphysics is, hey, we can get an absolute epistemology that simply describes ontology and mathematical formula. And that just and that can be independently observed. Of course, this is where you get quantum mechanics, general relativity problems. But there's an independent, godlike observer that could script the laws of ontology at the very base, and that's the inevitable deterministic cause of being.
Yes, and this model is very prevalent. And like I say, that model and its shadow, the decadent romanticism that fills popular culture, they pretend to be opponents, but they are sharing the same horrible framework that robs human beings of a capacity for genuine meaning and wisdom.
Amen.
So Greg pointed out the one kind of example is the person who discovers that they are only chemicals. I, of course, have met many of those people, but the opposite, of course, is the increasing prevalence of narcissism and spiritual bypassing in our society, which people retreat into their subjectivity and to their wonderful experiences at the expense of a rational responsibility.
There might be a quantum cosmic consciousness, John, that I'm tapping into, and then can be all as one.
Yes, yes.
Sorry, no disrespect, man, but that's the simplistic notion of that is also deeply problematic.
Right, and so for many people, if they get to this point, they feel like they're in a straitjacket. They feel like, you know, neither one of these works, and I'm going to argue that one can't work. The first one, the decadent romanticism, I've put enough criticism into elsewhere, right? But they'll say, well, this doesn't work because I can't really live as if I don't exist, and I'm somehow an illusion being generated. And who's the illusion being generated to, by the way? An illusion being created by a bunch of chemicals, and I can't really be, in touch with the world and other people if I'm doing this spiritual bypassing and narcissistic craze. But what we want to say to you is, you're not in a straitjacket. That's what this series is going to do. It's going to be sort of a philosophical Harry Houdini for you. It's about how do you get out of this straitjacket in a reliable and intellectually respectable way. So what I want to do is I want to start making...
That's a very appealing proposition. I'm not going to lie. It's a very, very appealing proposition because I've felt that myself, but I'm also not going to lie. I'm a little skeptical. And this is why, we need to go several layers deep in terms of unraveling what our presuppositions are, because it's easy to just settle in some kind of simple framework for thinking about things, and life isn't simple, and you don't need things to be so complex to live a life, Not everyone does. But, depending on how closely you look at things, you might need a little more. So, I'm interested to hear what they have to say, and I'm going to keep playing the video.
An argument, or reviewing an argument, that I've been making over the last 3 or 4 years, and it's sort of been building for me, I hope, in clarity. It's because it's been helped by some amazing people. And I want to go over that argument. I want to set up a few preliminaries. I'm going to put one preliminary, Greg, in that I didn't put in for the Consilience talk. Okay. Let's do the first 2 preliminaries.
Okay.
First, I'm going to propose that if we can make a strong case, a good case for strong transcendence, then we will have given people the beginnings of the way out of that. Now, you, of course, are going to link that strong transcendence to a worldview, but I'm going to do my part of it by making a proposal for my part in our partnership of making a proposal for strong transcendence. And what I mean by strong transcendence is that those experiences in which I'll try and say this as neutrally as possible. When we have those experiences, and they are experiences that we are transcending, these are not experiences of just psychological improvement. They are experiences that have significant and important epistemological oomph to them, and they have ontological teeth to them, and they are really disclosing important aspects of reality, and therefore they are not merely subjective improvement. That's what I mean by strong transcendence.
Okay, let's hear that again. So he says transcending significant and important epistemological teeth was, I think, the words he used.
Are not merely subjective improvement. That's what I mean by strong transcendence. Ontological teeth to them, and their epistemological oomph to them, and they an important epistemological oomph to them.
Oh, he said epistemological oomph. It's a technical term, oomph.
And they have ontological teeth to them, and they are really disclosing
Ontological teeth. In that they are really disclosing
important aspects of reality, and therefore they are not
important aspects of reality.
merely subjective improvement. That's what I mean by
They are not reporting merely subjective
oomph to them, and they have ontological teeth to them, and they are really disclosing important
not reporting, disclosing
to them, and they have ontological teeth to them, and they are really disclosing important aspects of reality, and therefore they are not merely subjective improvement. That's what I mean by strong transcendence.
Maybe we should.
Yeah, go ahead.
Like when we talked about this and did our 11th problem of consciousness, the 2 blogs on that.
Yeah.
I think we just allude to when people are having transcendent experience. One way to think about this is a transformation in their self-world grip. That their model of what, and then there's an expansion in that mode of being. So the frame in which people are bringing to bear, they gain insight to. There's a shift, a melting, as it were, and a reconsolidation. At least that's sort of one way to characterize some of the cognitive schematic elements of a transcendent mode.
Yes, I agree with that. What I want, and I think that idea about a mode of being is going to become very important. What I want to say is that there are important truths about reality, and not just about one's psyche, that are disclosed in strong transcendence.
Okay. There are important truths about
that are truths about reality. What I want to say is that there are important truths about reality, and not just about one's psyche.
Important truths about reality, and not just about one's psyche.
That are disclosed in strong transcendence. That would be the difference. Now, it's not clear if this is an accurate reflection of Jung, especially not the latter Jung. But many people read Jung as talking about all these experiences, but they're ultimately only happening within the psyche. Right now, I know. Don't jump on me if you're a big Jung fan. But what about the psychoid later? I'm already qualifying it. I'm just saying. I'm just trying to give people an easy example that would come to mind.
So what I would say is, how do you make that distinction? Like, if you're going to say that there are strong differences, but you're not going to belittle the psyche, that is the imperfect agent's experience in the world, with all the issues that come with just having the limited capacity to understand things. How are you going to make the case that the strong transcendence is disclosing significant things about reality? Like, significant to whom? Significant to what? I mean, like, are we just still invoking the same agent that we're saying we would otherwise be dismissing? Like, it still seems that we're, like, what he's talking about would just be important to the individual. So how are we establishing importance in terms of some, if not objective standard, then some standard that is bigger than a psyche? I'm having trouble with. So maybe we can get more details.
Kind of, oh, right, there's these, I mean, I remember when I was a kid and I read Fifth Business and Robertson Davies, and I was introduced to Jung, and it was the notion of the self and all of this, and then I had this, well, that's God, and I thought, but wait, that's just all happening in my brain, and my brain is this little bit of matter on the earth. That's not God, right? And right, and so I mean, again, I'm not here to caricature Jung. I'm just saying, you know, it's a logically possible world that many people do think of these experiences as just psychological experiences. The only truths disclosed are truths about the psyche. It could be the archetypal depth, but nothing about reality per se. And I think that's at least fair for at least to middle Jung, because Jung is such a Kantian, and he's so much locked into that framework. Okay, so we've got a clarity here. Strong transcendence. The reason why I think strong transcendence is central to spirituality, because that strong transcendence gives you a capacity for qualitative self-correction, for real transformative experience, for the cultivation of wisdom, etc. Deeper.
Okay, he just said a bunch of words that I know he talks about elsewhere, but we're going through this piece by piece because we want actual truth, and we don't want people to get away simply with invoking jargon and feeling like we're getting real information. We want to be critical. We want to be trying to get to actual truth, not just jargony truth. So maybe there is philosophical depth here, but that's what we want. We don't just want jargon. We want depth. So
for real transformative experience, for the cultivation of wisdom. I think strong transcendence is, we've got a clarity here. Strong transcendence. The reason why I think strong transcendence is central to spirituality.
okay, he says the reason. Okay, here's a quote. The reason.
A clarity here. Strong transcendence. The reason why I think strong transcendence.
The reason why I think strong transcendence. I don't remember how to spell it.
Transcendence is central to spirituality.
Is central to spirituality. Why are we talking about spirituality? I thought we were talking about getting out of the Newtonian Kantian straitjacket. So I don't understand why we went here, but I think he'll maybe contextualize it. I'm just not sure why we're talking about. Maybe he's saying the reason why strong transcendent ought. Maybe he's making a normative claim. Like it ought to be central to spirituality, and here's why. Central to spirituality
because that strong transcendence
is maybe it was a misspeak. Is because that strong transcendence. I think my computer's going to keep messing up. It's pretty annoying.
Gives you a capacity for
gives you a capacity. So this is like a pragmatic claim, right? Like it well gives you a capacity. Well, it gives that strong transcendence gives you a capacity
qualitative self
for qualitative self
correction
for
real transformative experience for the cultivation of wisdom.
For the cultivation of wisdom,
etc. Deeper experiences of
etc. Deeper experiences of
meaning, etc.
Meaning. I don't really know what he's saying here. Correction of real transformative experience. This feels like a lot of buzzwords, but I think it's more a matter of he knows what he's talking about. And he's talked about these things elsewhere, so he's just invoking them. He's importing them into the conversation. But this sentence in and of itself, I think, is needs elaboration. For instance, well, right now he's talking about spirituality. He's not talking about escaping the Newtonian Kantian straitjacket as referred to above. So, yeah, we need are we saying that strong transcendence is important for spirituality, or are we saying that strong transcendence is an important, what's the word, for a thing, antidote to the Newtonian Kantian straitjacket? Is that what we're saying?
So is the strong, John, for us? And I think so, but let's be clear when we utilize that term, especially, by the way, it's going to
Yes,
we'll have to
please be
differentiate from
clear.
strong emergence maybe down the
Yeah,
line.
yeah,
that
yeah,
happened in
yeah.
Consilience
Yeah,
conference.
yeah.
We'll be clear about that. When we say strong, are we saying then not just in the psyche, we're really talking about the nature of reality and knowing and being as
Yes,
such,
yes.
that's going to require us to think about this more expansively than
Okay, so when they say strong, it's not just in the psyche, but in reality itself. And we're assuming that this framework is not a strong solipsism because they mentioned solipsism earlier in the video. So we're assuming some kind of interactionism. I don't know if that's an actual thing, but it's a word I'm using, like between individual and the world. Okay? And this is what they're calling strong transcendence. Oh my goodness. What did I say? My stuff is going to keep messing up. Not sure why it's doing that, but I do want to get through a little more.
just reorienting the psyche's grip on the world within itself.
Exactly. And my argument, although I won't push too much on this part of the argument today, but you can see it in other work I've done. You can see it in Convergent work, for example, in Aspects of Truth, the book you held up, right? That this is the notion of transcendence in the pre-Cartesian world. There is psychological transformation, there is psychological improvement, but there's also epistemological and ontological improvement in a very real way. Okay, so I next want to propose extended naturalism. I'm going to propose it, and then we'll defend it along the way. Extended naturalism is the idea that your ontology is not limited to what is just derivable from your fundamental hard sciences, but it is also derivable from what is presupposed by your hard sciences, and that means not just by your, it is also derivable from what is presupposed by your hard sciences, and that means not just propositionally, but performatively so. For example, I am going to take it that some of the presuppositions in the hard sciences are that the hard sciences really exist, they're not illusory entities, and that they gain real knowledge.
Okay, so he's going to propose that sciences get real, discover real, there's that concept, real knowledge, and he said discover, not create, but discover. So if my understanding is correct, if you are constructivist, that means all knowledge is constructed, which I'm not really sure what that makes, like how that is differentiated from like a world where there's relationships, where individuals are relating to the world. And I should just say, like, because Buddhism got in here young, like the idea of interdependent origination, like form is emptiness, emptiness is form, like everything is sort of dependent on every other thing. These ideas got into me pretty young, and I haven't found compelling arguments against them. I think the most compelling arguments might be that it's an irrelevant point as opposed to it's not a true statement. And even then, I would need more details. I haven't heard, once again, I haven't heard any arguments against it. But so this seems to track with that idea. So he's going to propose that science discovers real knowledge. Not sure what that really means when we say real knowledge, because I think he means more than just knowledge that can be applied for effects in the world. I think he means more than that, knowing him. So
is really exist, they're not illusory entities, and that they gain real knowledge. Those are the only two presuppositions I actually really need for my argument. And I think a denial of those would be extremely problematic for anybody who...
A denial of those would be really problematic. And I mean, I think I agree. Like, I said this before, even before I saw this video come out, that I think a lot of my foundational thoughts do necessarily depend on biology being a real thing, like presupposing the truths that are discovered in biology. And sort of going from there. So I think he's basically saying a similar thing, which, you know, feels good. But obviously, you know, I've been influenced by him, so it would make sense that it would connect. But then we're both influenced by Buddhism, so that's probably playing a background role as well. So, you know, let's keep going.
Wants to invoke a kind of scientific worldview. Now, one thing I want to... that I didn't do at the conference is I want to make an argument about reductionism. It's not actually my argument, it's Ned Block's argument. And you sort of touched on it a minute ago, Greg, which is once you start reductionism, there is no reason in principle where you can stop at any level but the very, very bottom level. This is called, right? And he says, look, any move you say, oh, this, right? Then if there are possible levels below that, then you're compelled to drop and drop and drop and drop and drop to your possible level. That's the third thing I want to just put on the table. And I think for those who want to, you know, if you want to examine that argument more carefully, just take a look at Block's work. But I think that's a fundamental move. Once you open the door of reductionism, see, you get this problem with people very often. They'll say, oh, well, it's all just in the brain. Well, you can't stop there. There is no, right? You have to keep, well, what's in the brain is just the molecules, and what's in the molecules are just the atoms, and what's in the atoms are just the quarks, and what's in the quarks are just the more fundamental whatever they are, and what's in those is just the probability distributions, and what's in those is just sort of, oh, right, and you get down, right? And so I'm not going to allow any reductionists to stop at any level other than the very, very bottom level.
Lovely.
Okay.
Yep. No, and I'm with you, and I'll throw out a little U-Talk teaser here to come back to this, okay? Which basically says,
I think the counter argument, I mean, I think a reductionist would bite that bullet, and then they would have to counter the more convincing argument here, which is that, well, then science is just probability distributions at the base. And even then, like, you might be able to buy that bullet, but then to what degree can you even claim that knowledge is real if it's just the probability distributions happening at the quark level? And then it's like, well, it's pragmatically that doesn't make any sense. But then you're saying, well, I mean, now you're invoking a whole different epistemic program by invoking pragmatism, and you know, that sort of comes to like the idea of like you know, determinism versus, you know, a sense of self-determination. Like there probably isn't actually self-determination, but we can certainly feel like there is. And, you know, just saying, well, in order to exist, I have to assume these things that are necessarily wrong, you know, like that I have will and the ability to determine my own life, that is inherently unsatisfying. Like, it may be necessary, but it's unsatisfying to say that in order to, like, the actual truth may run counter to my own project of being an organism in the world. that I have to rely on a lie in order to live experientially a good life, if that any of that made any sense.
One of our little mantras in UTalk is I am an energy information singularity, and it actually allows you to grab all the, it does afford. Now think about it this way. Remember I said I'm just a bunch of chemicals. I'm an unfolding wave of energy information. Okay. And I'm going to suggest that the concept of energy information is one of those ontological concepts that affords, if we're going to go to the bottom, okay, those are two pretty good words that get you to the bottom on the one hand. Now, of course, you and I are in 100% agreement that you will not explain the world from the bottom without emergence and emanation.
Yes.
But we certainly don't want to stop at chemicals or quarks. But energy information is actually an interesting place to bottom out on, and it can be a fun place to bottom out on as you climb back up.
Yeah, and I want to. A lot of my argument actually runs off the idea of needing information to be real
Exactly.
in a very fundamental way in your
In a
ontology.
very fundamental way. And energy is pretty real too.
Well, the two are inseparable from each other in an important way.
Well-
Especially if when you get down to the bottom level and all you're talking about probability distributions, and then where's the fire in the equation? Where does the actuality come from? And we can talk about that when we get to it. But
Amen.
are we sort of
Anyway.
set up? Are we sort of
Totally set up. 100%. Yep, I'm there.
Okay, so we've got these three things. We've got a proposal for strong transcendence, a proposal of extended naturalism, and a proposal that you can't stop reductionism except at the very, very bottom.
Okay, so three things. One, strong transcendence. Two, extended naturalism. And three, can't stop reductionism except at the very bottom.
Level. And maybe there is no such thing, and then that also becomes very, very problematic as well. All right. So what I want to do is review the arguments, and I'll take a bit of time here to do something I didn't quite do as well at the conference. I'm glad it was very well received, but I came away thinking I should have done this, and I should have done that, and I should have done that. Right? Typical academic. Okay. So there's going to be two convergence meta arguments. What do I
Actually,
mean?
everyone, so I'm sure people know this, but this is Leveling Up at the Utah Concilians Conference. But you named it on your channel. What was it, like Neoplatonic Science and Spirituality or something?
Yes,
Just so
yeah,
we'll make
yeah.
sure we should put it in the show notes just in case
Yeah,
somebody.
we'll put it for sure. We'll put
okay,
it for sure.
just wanna make
I recommend we. Yeah. I think. Do you have it anywhere, or is it just on
Yeah.
my channel? If it's just on my channel, we'll just put that link in.
I mean, you can find it on my UTalk circle. We'll put it on your channel. That's the right place to send people.
Okay, great. And so I'm going to do two, and maybe we'll just get through the first one today, maybe a little bit more. We'll see. Greg and I want to be really sort of flexible around this because we want to go really slowly on this because I think Greg is right. This is the culmination. It doesn't mean this is the last thing we're going to do together, but it's the culmination. This is really the fulcrum point of everything else we've been doing, which is why we didn't do it first, right?
Yeah, there's a lot of territory to clear and make sure we were syncing up on before we tackled this thing. for
Yeah,
sure.
this is the dragon in the stormy sea. So, what's a convergence meta argument? It's an argument made up of.
Okay. What is a convergence meta argument? And I assume he's going to say an argument made up of other arguments?
Arguments. So what I mean by that is that there are many independent arguments that converge on a conclusion. So it's an argument out of arguments, a meta argument, and it does convergence. Why is convergence important? Because if you have many independent things converging on the same conclusion, then that raises the trustworthiness of your conclusion. Because what it means.
Many arguments converging, then it raises. He's using trustworthiness in a specific way. This trustworthy raises the trust. I forget who it's from, but trustworthiness of the argument. Trustworthiness is a technical term. And the real question is, do those arguments actually converge or not? That's the real question. So he's arguing that certain arguments do converge on a single conclusion. Whether or not that's in the case can probably be disputed, but whether they can be disputed in a certain way. I mean, the issue here is that any particular argument that is dispatched of it makes it harder to disprove this so-called meta argument, right? So if we get rid of one argument, that may be falsified, but then he's still going to be able to point to the other arguments and say that these are in fact still all valid. So even if one is wrong, that may weaken it a little bit, but it's like the head of the Hydra, you know, like it still seems to point to a certain direction. So the real question is like, how many arguments would one need to dispatch of to really weaken this case? Are the arguments true? And if not, you know, how many do we need to get rid of to really weaken the strength of the conviction? And, you know, does it make sense, the case he's putting forward for whatever these arguments are? Now, he's pointing to, I think, his previous work with Greg Henriquez, which was like Untangling the World Knot and the Self. There was something about the Self. And those were all a lot of, I haven't gone through those, like I listened to them in the background, but I haven't really cut my teeth on them. But I think those are the arguments that they're pointing to. So the real question is, do we buy those other arguments? Because if we do, then this is the case they're going to be making in this series.
Is it's very unlikely that your conclusion is produced by the bias of this argument or this argument or this argument or this argument. It's very important that those arguments come from other people than yourself, which they are, because that also increases the trustworthiness and the plausibility. And then I attempt to show what's the elegance that comes out of that is that these two meta arguments can be put together so that there's a convergence between the convergent meta arguments. So the first argument will be an argument about reality not being flat land, not being just all that's real is just the very, very bottom, and everything above it is illusory or epiphenomenal. And we'll talk a little bit more what that means. And then the other convergent meta argument is towards a conformity theory of knowing. Opposed to a representational theory of knowing. And then when you have those two, they fit together as they had in the past to give you strong transcendence within extended naturalism. And that's the proposal.
And in the talk, and I don't know if we're going to frame it exactly this way, or if you then added the third argument of transjectivity. Yes. In terms of whether, and that in some ways emerges out of the two, but it also ties it together very nicely in relation.
I thought I presented it. Maybe I didn't do a well enough job. The transjectivity argument, I think, was part of the argument. Well, I'll do it that way, though. I think I like the way you did it. I was seeing the transjectivity argument as part of the conformity argument, but that's
you sort of in the talk you actually sort of framed it both ways, but you did then round it out as a third meta convergent argument.
Okay, well, good for me.
Well, I thought it came together well, friend.
No, let's do it that way. Let's do it that way. Okay, so the first argument is why you need a leveled ontology. This is the idea that actually, in the end, what you're going to have is a continuum, and the levels are just where you happen to slice it for various epistemic projects. But the main point is it's not a flat ontology. So the main first argument, it comes from Blackowitz in his really excellent book, The Essential Difference Towards a Metaphysics of Emergence, and that's from 2012. And let me see if I can do this argument a little bit more intuitively. And the basic idea is how reductionism works is reductionism says it's only the properties that things share that are real. So let me give you an example. Here's three things, right? And they obviously are different from each other, but what they all share is that they're all made out of matter. And therefore what's real about them is how they're made out of matter, right? And this, of course, is why people invoke things like materialism as an ontology. Nobody in science believes in materialism. Nobody believes that all that's real is matter. That's kind of a crazy claim. But nevertheless, that's the name that has historically stuck with it for that reason. One of the most obvious things we can do is say, what they all share, what they're identical in is this underlying thing, and that's what's most real. Why do we do that? We do that because if I know the properties of matter, I don't need to have to know the individual properties of this and this and this, so I can make general predictions about things.
Generalizations, exactly.
Generalizations. Now here, notice what's happening, and please pause to note this. It's more real because it increases my capacity for explaining, which means my judgments of realness are precisely calibrated to the increase in intelligibility. Realness is tracking intelligibility. Okay, and that's what's justifying this, that profound intuition. And I'm not going to try and justify it, because if you challenge that intuition, you're really into skepticism, right? That realness is tracking intelligibility. Okay, now what does Blackowitz do with this? Well, he says there's a problem with that, which is, couldn't it be the case that the differences between things are also essential to their intelligibility? Right? And you go, what? Well, why might that be the case? Well, first of all, think about the problem with generalization. This is one of the trade-offs that we've discovered. That generalization is always in a trade-off with discrimination.
Yep.
If I generalize generalization is always in a trade-off. Generalization. This is one of the trade-offs that we've discovered. That generalization is always in a trade-off with discrimination.
Yep.
If I generalize and I lose too many important differences, I actually lose a grasp on the causal grip of reality. And that's also part of what we mean by real.
Yep.
Right? So let me give you an example. Here's two predictions I can make. There's stuff near me, right? Or there are people near me. Now notice the one is
Okay, this is where I have to leave it because I have an appointment soon, so we're gonna stop streaming now, but this has been very interesting. Once again, if you are enjoying this content, please hit that like button, hit that subscribe button, and eventually pay me your money, because I deserve it and you deserve it. It is something you deserve for yourself. Treat yourself to my content. Thank you for hanging out, being my best bud, and I look forward to seeing you next time. Maybe later today, maybe tomorrow, maybe next week. I'm not sure when I'm coming back, but rest assured that I intend to keep putting out this content, talking about intelligent things, figuring out this whole streaming shenanigans, and I look forward to seeing you next time. Thank you so much for joining me. I will see you next time. Peace.